and he's going to be acting for 2 weeks.
Oh, nice.
Oh,
Okay, so I think that more or less we can start.
Okay.
So just a reminder to all the attendants, please to mute yourself and stop your video. So now Professor Maruno will introduce today's speaker, and please go.
Okay, so welcome to the seminar. So today's speaker is Professor Cheng Zhang from Shanghai University. So title of his talk is on the inverse scattering transform for integrable PDEs on the half line. Okay, please.
Okay. Yeah. So first of all, I'd like to thanks the organizing committees for giving me the chance for this talk. So the title is about inverse scattering transform for integral PDEs on the half line. So we are dealing with boundary problems on the half line with a boundary. So basically, the key idea is to think of the problem, what kind of integrable system can be solved by inverse scattering transform. So how we can tackle this problem with the boundary. So this work is in collaboration with my master student Wang Zhongyuan. So sorry. So basically, so when we are dealing with integrable models, the boundary or asymptotic behaviors are actually crucial in defining the integrability. So the easy example, for instance, for two-dimensional integrable PDEs, we have periodic boundary conditions or quasi-periodic boundary conditions. So the periodic boundary conditions for the real field, for example, for the KdV field, the quasi-periodic boundary condition for the loneliness Schrodinger field are the general and the natural boundary conditions. So the boundary conditions is somehow in brackets because there's no boundary. So if you consider the periodic problem. So let's look at the periodic problem. So basically the space variable is defined on a circle. So we can extend this circle to the whole axis by defining a fundamental domain to be from 0 to L, for instance. So then the problem on the full line can be thought as a periodic problem by extending the fundamental domain to -infinity to +infinity. And the idea of inverse scattering transform or conceptually similar method called finite gap integration method are known to be the systematic approach to solving initial value problem for this kind of models. So let's look at a concrete example. So let's take the loneliness Schrodinger equation as our primary example. So the equation defines like this. So this is the focusing analysis equation. Q is a complex field. So let's first impose the periodic boundary conditions. So the Q repeats itself with the length of L. The analysis equation admits the Lux pair in this form. So we have 2 by 2 Lux matrix, and the Q is encode this potential, this NLS field, and the sigma 3 is the standard Pauli matrix. So we will call this U and V in this talk space part and time part of the Lux pair. So they are polynomial in the spectral parameter lambda. Okay. So when we have the Lux pair, we can think to solve the problem. So the key notions, the so-called transition matrix or monodromy matrix. So the transition matrix, or in ODE we call it fundamental solution, they are the solutions to the space part of the Lax equations. It's actually the formal integration along a path from 2 points on the axis. So it's defined this way. Okay, so this order is actually a ordered exponential. So by definition, we have these properties of this transition matrix. And the monodromy matrix is actually the transition matrix with the path of integration going along the fundamental domain. So for instance, for the periodic problem, we have the fundamental domain from 0 to L. So that's the monodromy matrix. So it's going along the space domain as a loop. So basically the monodromy matrix, the path of integration of the monodromy matrix is going through a loop. That's what we showed in this picture, in the previous picture. So it's going along a loop this way. Okay, so when we have the monodromy matrix, the idea of monodromy matrix actually connected to the monodromy in ODE. So monodromy is basically a loop around the singularity. So we borrow this name here. So in physics or in analysis, sometimes we call monodromy matrix transform matrix or Gathering matrix. Okay, so having the monodromy matrix, we can naturally have a Lax formulation for the monodromy matrix. So by derivative of the monodromy matrix with respect to the time variable, we have this Lax formulation. And having this Lax formulation, so the trace of monodromy matrix can be considered as the generating function for infinitely many conserved quantities. And to solve initial value problem, for instance, for the periodic problem, the idea of inverse scattering is to formulate a scattering system for the based on the Lax system, based on the Lax pair. So in this case, we define two fundamental solutions, F and G. So by definition, this F and G can be solved. So if you consider interval from 0 to L. So F is integrated from L to certain point X. So you have a F, and the G is integrated in another direction from 0 to X. So this is G. And these two as the fundamental solutions, they are connected by the monodromy matrix. And in this particular periodic problem, this F, this fundamental solution G can be thought as the fundamental solution F acted by a translation operator TL. So just by construction, we can show that. Then the analytic approach for the periodic problem known as finite gap integration method is to determine possible spectral properties of this Gathering problem, and to determine most general analytic expressions of the fundamental functions, fundamental solutions, and inversely to solve this periodic problem that gives solution to the NLS with the periodic boundary conditions. So that's the idea. And so when we are dealing with the problem on the whole line, so basically we extend this periodic problem. So we extend these two ends of the interval to infinity, to plus or minus infinity. Then this F and G, and under the vanishing boundary conditions, so let's assume this Q decay fast enough when X go to plus or minus infinity, then this fundamental solution act freely. So they are known as the Yost solutions of free waves. Okay, then the scattering system is iterated from the periodic problem. So we have this T monodromy matrix for the whole line problem, and it has the Lax formulation when X when x go to infinity, we have the fast decaying behavior of the NLS field. Then the scattering data behaves quite simple. So we have the A matrix, the diagonal part of the monodromy matrix, a constant is preserved by the time evolution, and the anti-diagonal matrix act in this way. So basically, we solve the ODE. So with presumed scattering data, we could obtain analytical expressions of the fundamental solution and inversely give the solution to the NLS equation. So in general, initial value problem for NLS, for frequency NLS, are a very hard problem. But in certain cases, we can obtain, for instance, multi-soliton solutions, or in certain cases, we can use the nonlinear steepest descent method to study the large time asymptotic solutions. So that's the picture for the periodic and the problem on the whole line. So basically, these two problems, there's a common feature. So there's actually no boundary, because if you think the space variable defined either on the circle or on the whole axis, so there's no boundary. So the initial value problem for the NLS on the whole line is essentially equivalent to the periodic problem. So we have, so the equivalence is what we showed to extend the fundamental domain of the periodic problem to infinity. So for this whole line problem, this plus or minus infinity actually merge. So then you have the periodic picture of the full line problem. So this aspect is well captured by the review paper by Khrushchev and Novikov in 1999. So they said, let's point out that the KDV system or large class of integral PDEs can be integrated by the inverse scattering transform. So they are indeed completely integrable in the sense of rapid decaying behavior of periodic boundary conditions only. So you can't. So basically, the integrability is encoded in this periodic behavior. So then, if we go to the integration technique, the inverse scattering transform is actually somehow related to simpler mathematics than the periodic problem. But that can be integrated by the finite gap integration. That is because in the full line problem, you have this point at infinity, which give rise to Yost solutions. For the periodic problem, you have to go to the spectral curves, and your spectral parameter is naturally living on a compact Riemann surface. Okay, so in this talk, I would like to deal with problems with a boundary. So what we really called open boundary problem. So you have your space domain with a boundary. So you have for two-dimensional PDEs, you have either half-line problems, so you have a one boundary, or interval problems. So your space variable is restricted on the interval. So the questions are how to solve such problem, the problem with a boundary, and what are the admissible class of boundary conditions. And physically, so if we think this integral PDEs represent certain physical phenomena, so what are the possible implications in the presence of a boundary? So some general motivation to think of boundary problem or initial boundary value problem is actually, so boundary problem are actually related to the aspect of integrability. So in both case with or without boundary, we need to control what happens at the boundary. So in other words, boundary conditions are related to the integrability of the problem. So in the case with boundaries, so half-line problem or interval problem. So since we are dealing with integrable PDEs, so the natural approach is to look for integrable boundary structures, so what we are called integrable boundary conditions. So on top of that, well, real physics we know real physics system have boundary or boundaries, and a theory of integrable system with boundary can help at least qualitatively certain nonlinear boundary problems. So which are actually hard problem because we need lots of analysis to tackle nonlinear boundary problems. So there exists certain systematic methods for boundary problem. So one is developed by Focus, which is called Focus Unified Transform. So which is a general analytic framework to dealing with initial boundary value problems. Well, the key idea is based on simultaneous treatment of the space and the time part of the Lax pair in the direct sketching process. However, in focus methods, there's some problems. So first of all, there's no notion of integrability in focus method, and there's also lack of exact solutions in focus method. There's another approach developed by Skrianing. So actually Skrianing's idea is connected to the quantum integrable system. So based on what is called quantum reflection equation. In Skrianing's approach that I will present later, so there's very precise notion of integrability. So what he characterized the so-called integrable boundary conditions. However, in Skrianing's approach, there's a lack of analytic approach. So there's no inverse scattering transform exist for integrable boundary conditions. That is lacking in the literature, and that's the aim of this talk. And just a remark, in quantum models, the boundary problems are much better understood than the classical part. So partly because in the classical PDEs, there's no solution method, there's no analytical method. So for the NLS equation and the certain related model on the half-line, so actually you can solve this problem. So one is developed recently by Biondini and Wang. So they use what is called nonlinear method of reflection, which is the nonlinear version of the method of reflection for solving linear PDEs on the half-line. So the basic idea is to use the extended Lax pair. So the Q is an extended potential. The H is the Heaviside function. And if you use this Lax pair, you will recover a half-line problem with Robin boundary conditions. So, however, this method can hardly be implemented to other nonlinear boundary conditions, and it's not easy to generalize this method of reflection. And recently, there's a method called dressing the boundary, developed by myself. So it's an effective method to obtain exact solutions. However, it's not easy to generalize this method neither. So so there are some extra motivations to study the boundary value problem. So for instance, if we consider this GP equation, so we have the nonlinear shorting part with external potential, which is a delta potential. So if the initial data is even data, so we can show that the above GP equation is actually equivalent to nonlinear shorting equation with Robin boundary condition at the origin. So this actually gives some physical motivation of the half-line problem. And there's certain what is called dynamic boundary conditions in this form. So they are fully nonlinear boundary conditions, and these boundary conditions were obtained by Zhang. So they are fully nonlinear in boundary conditions that are integrable. So this model, the half-line NLS model with these boundary conditions, were recently solved by these two guys. So so in this talk, so what I claim is to provide an overall satisfactory answer, actually to develop the analytic approach based on Skrianing's idea of integrable boundary conditions. So in other words, so you have the half-line problem, which is integrable. So you have integrable boundary conditions. So we provide an analytic method, the inverse scattering transform, to solve this problem. And we also develop a notion of hierarchy of integrable boundary conditions that we'll show later. And these methods actually can include what I showed previously, the nonlinear method of reflection and the boundary dressing method. And we also set up the foundation for solving the interval problem, which is not known before. Okay, so here is the content of the talk. So first, I will show Skrianing's idea of integrable boundary conditions. What he said, the double row monodromy matrix. Then, based on the Skrianing's idea, I will show the hierarchy of integrable boundary conditions. Then the analytical method to solve this half-line problem, and show some soliton solutions on the half-line, and conclude at the end. Okay, any questions? Okay, so if you have any questions, please interrupt me if you want. Okay, so so the Skrianing's idea to deal with boundary problems, or a problem on the interval, is based on what is called the double row monodromy matrix. So the double row monodromy matrix is defined in this way. So graphically, it can be presented, which is shown here. So you have certain matrix, what is called reflection matrix, K plus or K minus, which encodes the boundary conditions at the two ends. And you integrate your monodromy matrix, your double row monodromy matrix actually is an integration follow the path shown here. So you actually form a loop which circling the interval. Then you start with your boundary matrix, the reflection matrix K plus, and going this way with T minus, and the K minus encodes this K minus and the T. So this is a double row monodromy matrix, and there's a key ingredient here is the change of parameter. So after the reflection, after the action of the reflection matrix, you transform your spectral parameter from lambda to minus lambda. So this is the key feature for the NLS model of because you can think this change of lambda as your solutions bouncing with bouncing of the boundary. So you change your, if you think lambda is related to the speed of your solution of your soliton, so you change actually your soliton solution, the speed of the velocity of your soliton from with a sign change. So with the definition of double row monodromy matrix, so the integrability criterion is the following. So if your reflection matrix satisfies these two gauge type transformation, then your double row monojoin matrix amount to a lax formulation. So with this lax formulation, this indicates that the model under consideration is actually integrable. There are some essential properties of the reflection matrix. So the two reflection matrix can be treated separately because they are defined at two different locations. And the gauge type transformation for the K matrix, for the reflection matrix, can be thought as a semi-discrete type lax pair. So this is because your K matrix acting on the auxiliary field will deliver a discrete action transforming your spectral parameter lambda to minus lambda. And if you combine these two linear problem together, you will go back to this semi-discrete this representation. Okay. So while this form looks a little bit strange at first glance, but actually we can show that this is always true. So with certain assumption on the K, and then the reflection matrix, the determinant of the reflection matrix are time independent. So they're actually first integrals. And we impose the following normalization on the reflection matrix K. So now having these properties, the question is, giving the V, the time part lax matrix of NMS, what are the possible boundary conditions? So then with the normalization property, we can assume a general expression of kappa. Kappa is the determinant of the reflection matrix. So it's in this form. The beta assumed to be strict complex numbers with known zero, real, and imaginary parts, and alpha is a non-zero real. So this kappa satisfies the normalization property with extra parameter, the parity parameter plus or minus. So in other words, having the zeros of kappa and an extra parity parameter, we can characterize this kappa. So so this amount to the definition of the set of points D. So then we meant to solve this semi-discrete lax pair. So we want to solve this system. So we transform this K into a polynomial of lambda, and we plug this polynomial lambda into the lax pair. We want to see possible form of this L. And solving this L will amount to a hierarchy of reflection matrix and a hierarchy of integral boundary conditions. The hierarchy is in the sense that your L, your reflection matrix is has a polynomial dependence on the spectral parameter lambda. Okay, so before showing the hierarchy, so I will discuss the scattering system for the double row monojoin matrix. So the idea is quite similar to the periodic problem. So now you define two fundamental solutions, F and G, in this way. So T are the transition matrix, what we called before. So they are connected by the double row monojoin matrix. So this scattering system can be naturally obtained by considering this picture. And now the fundamental solution have the well-defined boundary behaviors. So if you put your FL equals 0, X equals 0, you have this, and you have the well-defined boundary behaviors of the fundamental solution. So actually your integral problem can be extended periodically to the periodic problem. So by the idea is, so before we consider the integral problem, so if you extend this interval to a periodic problem with another extension from 0 to -L, and with another set of T tilde. So you can establish the equivalence between periodic problem and the interval problem. So this will lay the foundation to solving actually the interval problem in the future. And your double row monodromy matrix admits this kind of symmetry. And so now if we want to solve, if we want to look for half-line problems, so a naive approach is to consider a half-line transition matrix in this form. So, but obviously this form fails because it doesn't capture the boundary behaviors. So our way to deal with half-line problems relies on the double row monodromy matrix by extending the one endpoint to infinity. So I will show this later. So now, well, I will show this notion of hierarchy of integral boundary conditions. So this is the semi-discrete Lax pair for the boundary conditions. So kappa is well defined by this set of points and parity parameter plus or minus. So to compute this K, there's a combinatorial aspect because the degree actually depends on this N and this M, and also on the parity parameter. So there's a remaining freedom of this K. So we fix this K to be this form. So in this diagonal matrix form, when lambda go to infinity. And although we haven't proved rigorously, so the boundary conditions obtained by this semi-discrete Lax pair are actually integrable. So the proof can be based on Hamiltonian formalism using a R matrix approach. So let's see case by case. So if we increase the order and to see the certain case of this hierarchy. So if you have the degree which is 1, so then you have m equals 1 and n equals 0, and you have two possibilities. So the parity which is -1 or +1. So for the -1, we recall these Robin boundary conditions which was originally obtained by Scagliani. And if we use this plus parity, so we obtain a K matrix in this form and the boundary condition in this form. So this condition haven't been fully considered before in the literature, but these boundary conditions are actually related to integrable defect conditions in certain contexts. So if we increase the order, we go to n equals 2. So we have several cases. So we can choose n equals 1 or m equals 2. We also have the freedom to choose the parity. Okay, so in these two cases, we can obtain the reflection matrix in this form and the boundary conditions in this form. So these two boundary conditions, the first one was actually obtained by Zambon in 2014, and the second one, the second boundary conditions looks quite similar to the first one, but they cannot be mapped between each other. So actually, these two boundary conditions belong to different sets of parameterization. And if we go further, so we choose order 2, but with a parity minus parity. Then we obtain what is called implicit boundary conditions. So in this case, your reflection matrix depends on A1, A2, B2, three parameters. And your A1, A2, B2 are constrained by this system, and your boundary condition actually reads in this form. So in this case, your B2 is subject to certain differential equations. So we can interpret this B2 as an additional field present at the boundary. So if we increase the order, we go to another case of implicit boundary conditions. You have A1, A2, A3, and the B1, B3. And A1, A2, A3 are constrained by this nonlinear system, and your boundary conditions actually read like this. So in this case, your B2, your B3 can be interpreted as the additional field. Okay, so let's go to the inverse scattering part. So let's recall the definition of double row monodromy matrix, what we showed previously. So our idea is to extend this arrow to infinity. Okay, so this approach will keep the integrability of the system and also have the scattering system, what we defined for the interval problem, valid for this half-line problem. So if we consider x is bigger than 0 and extend the arrow to infinity, and assume the initial data on the half-line belong to certain functional space with q vanish rapidly as x go to infinity. So there are certain choice to choose this k plus or k minus. So we choose the k minus, so this reflection matrix here belong to the hierarchy of the reflection matrix. So you will have so with different choice of kappa, you will have a different choice of the k and the boundary conditions. And we also engineer the k plus in this form. So diagonal matrix with 1 and the kappa lambda. So then this form will ensure that the determinant of gamma is 1. And this kappa, although this k plus is a constant matrix present at infinity, but it's actually deliver a discrete action transforming lambda to minus lambda. So that's the key part to form the scattering system. And if we follow the scattering system for the interval problem, we go to the half-line scattering system with f and g as the fundamental solution we defined previously. So now your f behaves like a free wave as your solution. Your g is behave as a free wave as well, but accompanied by the action of gamma. So they play the role of your solutions for the half-line problem, and we have the well-defined scattering system. Okay, so then making some normalizations, so we can transform this f and g, these two fundamental solutions, as this xy and xy admit integral representations. And using certain standard analysis of integral representations, we can obtain the following results. So your x and y can be splitted into a column vector. So your x minus means that this column vector is analytic and bounded as a function of the spectral parameter lambda in the lower up complex plane. Sorry. And your plus means that your column vector is analytic and bounded in the upper half complex plane. So then we have xy connected by the double row monodromy matrix in this way. So then from the definition of double row monodromy matrix, we can express gamma in this form. So this entry is AB, usually called scattering system. So your B, your function B here now plays a role of reflection coefficients in the Euro inverse scattering case, and your AB can be computed using the column vectors. So naturally, your A function is analytic in the up half complex plane, and your A star is analytic in the lower half complex plane. Due to the symmetry of the double row monodromy matrix, you have the symmetry of these scattering functions. Actually, this symmetry are crucial in defining this half-line problem. And we can also relate this A, B as a multiplicative Riemann-Hilbert problem with well-defined asymptotics of A, and the time evolution of the scattering data. So since we assume that the fields vanish as x go to infinity, then we have the Euro type of time evolution of the scattering function. So A is preserved by time evolution and the B evolve in this way. Okay, then by looking at this multiplicative Riemann-Hilbert problem, we can derive what is called trace identity for these scattering functions. So basically you express your function A in terms of B. So B actually encodes both your initial data and the boundary conditions. So there's some particularity here. So your A actually has a prefactor zeta. So zeta will encode your solitone behavior, but it also encodes the kappa, which comes from the integrable boundary conditions. So so this, and in the integral, so in the Euro inverse scattering case on the whole line, your integral go from -infinity to +infinity. But here we go from 0 to infinity, and with a different dependence on this parameter. So that is different from the Euro inverse scattering on the whole line. And we can also derive the conserved quantities. So basically we take the log of A, and the conserved quantities can be expressed in this form. So again, you have these conserved quantities coming from this bound state, this solitone data, and also the contribution from the boundary conditions. So this K comes from the kappa actually. So the subscript is actually on 2G, which means actually only half of the conserved quantities appear. So this is due to the half-line nature of the problem. For instance, if you consider the translation symmetry, so when you have a boundary at the origin, the translation symmetry is broken, and so on. So that's why you have only half of the conserved quantities. And having the scattering system and the column vector xy, actually you can regroup everything as the Riemann-Hilbert problem. So that is the formulation of the Riemann-Hilbert problem. So this part looks exactly like the Riemann-Hilbert problem for the NLS on the whole line, but with the novelty that the jump matrix, the entries of jump matrix satisfy this extra symmetry coming from the symmetry of the double row monodromy matrix. Then we can state that if we can solve this, well, if we can represent this the solution of the Riemann-Hilbert problem as the integral, then the solution Q is actually in this form. So by extending lambda to infinity and the 1, 2 as a 1, 2 entries of G plus. And the boundary conditions for this half-line solution at the origin is actually determined by an extra relation here, which is exactly the hierarchy of integral boundary conditions we assumed previously. So we have the kappa control the boundary conditions and the well-defined asymptotic in this form. So the proof of this claim is can be split in 3 parts. So the first part, well, by certain dressing method, we can easily show that this G plus, so this G plus here, satisfies the Lax pair of the NLS equation, and the uniqueness of the Riemann-Hilbert problem can be obtained by the normalization property and the well-behavedness of the jump matrix. And the boundary condition is actually can be shown in this way. So actually the jump matrix obey this extra symmetry, which inherited from the symmetry of the double row of the scattering data. And if we arrange this transformation to the original Riemann-Hilbert problem, we arrive at this form, and we assume that this S plus in this form. So basically, we have this part here, but add some factors, some dressing factors, and due to the uniqueness of the Riemann-Hilbert problem, solution of the Riemann-Hilbert problem, we can show that this G plus is equal to J plus at x equals 0. So then, because this equivalence, we know that S plus also satisfies the Lax pair of the NMS equation, and this amount to the property of this K matrix, and the K are actually determined by this semi-discrete Lax pair. So we actually show if we compute, if we solve this Riemann-Hilbert problem, the boundary conditions that are determined by this relation belong to the hierarchy of integral boundary conditions. Okay, so lastly, we can show some explicit solutions, so soliton solutions. So the Euro-soliton solutions can be expressed in this form. So for the NMS equation, so you have n singularities and zeros of the spectral of the scattering function A, equipped with what is called norming constant gamma J. So that's the solution for n. That's the solution of n soliton solution on the whole line. So now for the half line solution, you actually have a paired singularity, so paired zeros of your scattering function A, and with paired norming constants gamma and gamma J bar, gamma J tilde, and the gamma J and gamma J tilde satisfy these extra relations which characterize this boundary condition. So this kappa J, you can choose this kappa in your whole hierarchy, and actually this will give you explicit solutions of the soliton solution on the half line, satisfy the hierarchy of integral boundary conditions. So the proof of this last piece, the paired norming constants can be done in this way. So if we have this singular, if we have this Rj and R tilde J as zeros of A, then we know that this X plus and X minus are proportional to each other. They are related by the norming constants. So we have the bound state for the space part of the Lax matrix, and actually this gamma can be related to this B function, and due to the symmetry of the B function, actually we can show that this gamma J and the gamma tilde J star are related by this relation. So that's the key relation. So if you want to consider the n soliton solutions on the half line. Well, so here is the last slide. So I just show one simple example. So you have the two soliton solutions on half line satisfy the Dirichlet boundary conditions and Neumann boundary conditions, and that's the two soliton solutions satisfy the Robin boundary conditions of NMS equation on the half line. Okay, so let's go to the conclusion. So basically, what we have showed is the analytic method for the Skrianin's integrable boundary condition, integrable models with a boundary equipped with integrable boundary conditions. So this method, although we only study the NMS equation on the half line as a particular example, so this method can be easily generalized to a large range of integral models such as Sine-Gordon, affine total, Ablovis-Ladik, etc. And so by studying this problem, so from the point of view of integrable system, so the analytical method to the half-line problem is essentially equivalent to the whole line problem. as we showed, actually, we can extend this half-line problem to the whole line, and with the yield solutions similar to the whole line problem. And we can also, in certain context, interpret this half-line problem as a whole line problem with integrable defect condition at the origin. So the methods we present in this talk can be also applied to certain integrable defect problem. So although the boundary condition we consider here are kind of special because they are integrable, but in this framework, we are already able to tackle some fully nonlinear boundary problems, which was unknown, which were very hard problem. However, we lack full understanding of the higher order boundary conditions. They are full linear, and what are their possible physical implications. So last remark, consider the interval problem. So by using the periodic extension of the interval problem, actually we can we can develop an analytic method for the interval problem based on techniques for the periodic problem. That's the end of the talk. Thanks for listening.
Thank you very much for your interesting talks. So are there any questions?
Hi, this is Nalini speaking.
Hi, Nalini.
I was wondering about the analyticity result. I understand that you have analyticity on, say, for example, each of the two half lines. But I'm a little bit wondering about any domains that include the origin or the point that is at the boundary of the two half lines.
Yeah, that's a very good question. Actually, because if you consider the boundary problem, so the general idea of PDE is so you have the solution, then you want your solution approaching to the boundary, which as the analytical continuation of your solution. So that's the idea of PDE method. But here, since we are dealing with integrable models, so we assume certain smoothness of the solution. So your boundary conditions is actually compatible with your field on the bug. So in other words, so we for all the example we considered, we already assume certain smoothness of the solution. So there's no this kind of conflict in the sense of PDE.
I see.
Okay. Yeah.
Thank you.
Thank you.
Other questions?
Got a question. I would like a couple of comments on the soliton interaction in this half-line setting. Because, okay, I saw the figure, but I was wondering if you can actually prove, like in the regular setting, how these solitons are interacting, and if the boundary actually gives some difference. And because I think I recall that I recall the result you mentioned by Biondini and Wang. And I think they did something to show what happened. I think that maybe in the KDV, I don't recall if that was the KDV case.
In the NLS case, case. Well, this can be done because I'm using my pad. I cannot show this animations. Actually, you have the half-line solutions of these fully nonlinear boundary conditions. You can see the soliton bunching of the boundary, and the interaction, I think what you say is the space shift after interaction with the boundary and the shift of the phase, that can be done quite in the standard way. So because you have your scattering system well established, and you have all your analytic tools, so that actually can be done. But I haven't shown it here. So did that
I see.
answer your question? Yeah.
Yeah. And can you tell anything about the interaction of the soliton with the boundary? Is that like an elastic interaction, or?
Oh yeah, they are elastic interaction. Elastic in the sense that, yeah, I see what you mean. So there are several ways to think of it. So if you extend your half-line problem to the whole line, so what I explained is the end. So basically, we are dealing with a whole line problem with a defect condition at the origin. So the boundary condition, yeah. So then you have actually elasticity, yeah. So, and you can also show, you can using various methods to show actually the interaction is elastic. Yeah.
Okay, thank you so much.
Yeah.
Other questions? Maybe I have a question. So in this picture, there, yeah, this is two soliton solution, but there are four solitons. But
yeah.
For example, in the solitons in the center are actually same soliton. Is the amplitude is same? Like looks like pair. Is always outside one is also amplitude is same, but
okay, the amplitude is the same. Yeah.
Amplitude is same.
Amplitude is same because for this NLS model, the amplitude is controlled by the real part of your spectral parameter, which is the complex number. And if you change lambda to minus lambda, actually the norm doesn't really change. So the amplitude is the same, and the velocity, the norm of the velocity is also the same.
So looks like the actual boundary is the kind of wall. So then the wave, one is incident wave and another is reflection wave. So kind of
kind of. So the picture is really small. So you have the T here. So you have your soliton traveling here and reflected by the boundary. So the amplitude and the velocity is the speed is conserved actually.
I see.
They are conserved quantities.
So in this case, the solution is written in the form of determinant.
You can express them in form of determinant. Yeah. So you have the solution in form of determinant, but now you take the paired scattering data, soliton data, and you restrict your solution on x plus infinity, x plus 0, sorry, and then you have the analytic solution in this form. Yeah.
Okay. Yeah. Thank you very much. Yeah. So, are there any questions? Okay, so no questions. So I think it's time. So, okay, so now let's thank to Professor Cheng Zhang.
Thank you.
Thank you very much.
Thank you very much.
Thank you, Nandi. Yeah. Thank you.
A very interesting talk. So I think I will be closing the now and give you appointment to the next meeting. Okay. Bye. See you all.
Bye-bye.
Yeah, see you. Bye-bye. Bye. Bye-bye. Bye-bye. See you.
Bye.
Thank you very much.
Thank you.